For today's program, a telescope and a microscope won't be enough. We're going to find out about the four forces that rule the universe. We will also learn how we manage to control them. And lastly, we'll learn about leptons, gluons, quarks, and other subatomic particles with names just as exotic. The origins of physics, as for many sciences in the West, date back to the first Greek philosophers. The latter had already come to the conclusion that matter was an assembly of little blocks, and they called these little blocks atoms. The notion of atom then fell by the wayside, up until the 17th and 18th centuries when a few scientists took an interest in them again. One of them was Isaac Newton. But Newton became famous for other reasons. He studied gravity and developed the theory of universal attraction. Gravity is what causes an apple to fall from a tree and the planets to revolve around the sun. It was the first of the universe's great forces to be identified, but it isn't the most powerful. Let me introduce the three others. The radiance of the sun, the fury of a storm. Our world seems dominated by implacable forces. In ancient times, the unleashing of the forces of nature were ascribed to quarrels or acts of revenge among the gods. But modern physics teaches us that all these phenomena are ruled by four principal forces. As the planets make their journey endlessly around the sun, all the objects near the surface of the Earth are irresistibly drawn toward it. Both these phenomena are caused by a single force, gravity. According to the law of gravity, all objects possessing mass attract each other. However, that attraction is only noticeable when the object's mass is very large. The Earth is very massive and has a powerful gravitational field that keeps the moon orbiting around it. But the moon also exerts a gravitational force on the Earth. It's that force that creates the tides. An object's gravitational force gradually decreases as we move away from it, but it acts over very great distances. That's why even the planets farthest away from the sun remain prisoners of its attraction. The second force in the universe is electromagnetic force. Like gravity, it acts from a distance. Electromagnetism is at the source of phenomena as diverse as electricity, magnetism, and light. Its source lies within the very atoms that make up matter. Each atom possesses a nucleus that bears a positive electric charge. Around the nucleus revolve one or several electrons bearing negative charges. The electromagnetic force makes the opposite electric charges attract each other. Under its influence, the electrons swirl around the nucleus, a little like the planets around the sun. The electromagnetic force makes itself powerfully apparent in an electric storm. During the storm, large numbers of electric charges of the same kind accumulate in the clouds, whereas their opposite charges concentrate in the ground. For a brief moment, these electric charges surge toward each other. They create an electric current. This movement of the electric charges causes a second phenomenon, the emission into the atmosphere of an invisible magnetic field. That magnetic field has the property, for instance, of making a compass's magnetic hand deviate. Simultaneously, a third phenomenon occurs. During the storm, some electrons in the air's atoms are temporarily torn away from their nuclei. Small, massless particles, photons, then burst out into the atmosphere. Photons are the elementary components of light, which explains the blazing lightning we see during an electric storm. The light of the sun and stars, as well as the radio waves they emit, are also manifestations of the electromagnetic force. The third great force of the universe originates in the nuclei situated at the core of atoms. These nuclei resemble small blackberries. They consist of two types of particles, protons with a positive charge and neutrons with zero electric charge. Normally, protons and neutrons are stable. However, in some chemical elements referred to as radioactive, neutrons turn into protons or vice versa. The force which causes this transformation is called the weak force. Electrons emitted under the action of the weak force constitute a form of radioactivity called beta radioactivity. A number of these radioactive elements are found in their natural state on Earth. Researchers believe that it is radioactivity that is responsible for the intense heat that reigns in the depths of the planet. In turn, that heat generates numerous phenomena, including the slow shifting of the continents and violent volcanic eruptions. The fourth force of nature is the nuclear force, or strong force. It is the most powerful force of all. Also found in atomic nuclei, it holds protons and neutrons together. The nuclear force makes itself manifest naturally in our sun. The sun's fuel is composed of the nuclei of light chemical elements. Under enormous pressure and temperature, the two light nuclei fuse together. Considerable energy, caused by the nuclear force being exerted between the two nuclei, is then emitted. The sun radiates that energy into space in the form of light and heat, part of which reaches us. The four forces of nature do not only become manifest in spectacular natural phenomena, they are constantly at work around us. They presided at the birth of our universe and continue to ensure its existence. The four great forces of nature continue to baffle scientists. In fact, some daring physicists are trying to prove that these four forces are different manifestations of a single fundamental force. These high-flying, half-philosopher, half-poet physicists are convinced that the universe can be explained by one mathematical formula. However, other researchers are trying to take advantage of the knowledge we already have, and to them, we owe a host of very useful applications. For a long time, man remained subject to the all-powerful forces that rule the universe. Through the centuries, however, he learned how to control these forces and exploit them for his own purposes. Man has always attempted to fight the first force of nature, gravity. Though there is no technology that enables us to neutralize the gravitational force, we are able to annul its effects temporarily. Most of the devices that fly through the Earth's atmosphere can do so thanks to the air in the atmosphere which enables them to lift off and which holds them up. A rocket launch, which does not use the air, requires considerable energy. The rocket must reach a critical speed, called escape velocity, to tear itself away from the Earth's gravity. That velocity is 22 kilometers per second. If the rocket does not attain the escape speed, it will fall back to Earth. Gravity often obstructs human activity on Earth. In space, however, we have learned how to use this elusive force. Thanks to gravitational force, a veritable rosary of satellites now orbits our planet. These objects do not escape from the Earth's pull. A satellite which appears suspended over Earth is in fact falling freely toward it. However, its orbital speed was calculated precisely to offset its fall to Earth, so it remains hanging above our heads, where it accomplishes various tasks. The second force of nature, the electromagnetic force, has many applications today. Our contemporary society is largely built on it. It is the force from which electricity, magnetism, light, and numerous types of waves originate. In the picture tube of a modern television set, for instance, a metal element, the cathode, expels electrons when heated. The electrons carrying a negative electric charge are immediately attracted to electrodes which possess a positive electric charge. These electrodes accelerate the electrons and concentrate them into a fine beam. When the electrons hit the screen, the chemical products coating the tube emit particles of light, photons. The image on the screen is created via magnetic fields which direct the beam of electrons to sweep over the screen. The cathode's expulsion of the electrons, the latter's movements inside the tube, and the screen's emission of light are the results of electromagnetic force. It took men a long time to learn about the third force of nature, the weak force. It only reveals itself in the form of radioactivity. While it can be dangerous, this radioactivity also helps to save lives. Doctors, for example, use radioactive iodine frequently to treat a disease of the thyroid gland, goiter. In people suffering from goiter, the thyroid gland is secreting too many hormones, and this leads to disorders of the metabolism. The treatment of goiter consists of giving the patient radioactive iodine pills. The iodine is immediately absorbed by the thyroid, which uses it to make the hormones it produces. The atoms of the radioactive iodine quickly accumulate in the diseased thyroid gland. Through the weak force, the iodine atoms emit electrons that penetrate the gland cells and damage their genetic material. Within a few weeks, the thyroid ceases to function. Synthetic hormones will be used to replace the destroyed gland. Radioactive iodine is eliminated by the organism rapidly and therefore does not endanger the patient. Of all the forces of nature, it is nuclear force that creates the most apprehension. Scientists are still trying to find ways to use this force to produce energy safely. A solution might be nuclear reactors that would be much smaller than today's nuclear stations. Such nuclear reactors would have a water reservoir with a nuclear fuel at the bottom. In dividing, the fuel's atomic nuclei release energy. That energy heats the water in the basin. However, when the temperature of the water rises, the reactor's activity decreases. Because this type of reactor is very easy to maneuver, and because the temperature of the water never reaches the boiling point, it would be safer than the ones currently in use. It could, for instance, provide enough energy for a building or a small group of houses. We have a great deal more to learn about the four forces that rule the world, and their possibilities still hold quite a few surprises for us. Sometimes practitioners and theoreticians join forces to develop amazing scientific instruments. One of their most successful is the neutrinos trap. Neutrinos are particles that are smaller than atoms. Today, neutrinos are the center of attraction. But since the 40s, dozens of new particles have also had their moments of glory. We will show you some of these. How was our universe created? What is the nature of the matter that forms it and the energy that animates it? What is its destiny? And by the same token, what is our own? Such disturbing questions form the very basis of contemporary physics. By examining the infinitely small, physicists have discovered that the intimate structure of our world is very different from what we had imagined. Since the last century, physicists have known that all matter is made up of atoms. The atoms themselves are groupings of three kinds of particle. Protons, with a positive electric charge, are located in the nucleus of atoms. Neutrons, with zero electric charge, are also in the nucleus. The electrons, with a negative electric charge, gravitate around the protons and the neutrons. Until recently, physicists thought that these three types of particles, known as elementary particles, were the sole components of atoms and hence of the entire universe. But they reject that notion now. Using powerful instruments, particle accelerators, they have in recent years been able to probe matter more profoundly than ever before. Particle accelerators are based on the same principle as the picture tube of a television set. Elementary particles, such as protons or electrons, are first emitted by a source. They then reach a long tube in which a vacuum has been created. Under the influence of powerful magnetic fields, the particles are accelerated through the tube and projected against a target of atomic nuclei. The microscopic projectiles collide with the target with considerable violence. Detectors placed at that end of the tube immediately analyzed, on a microscopic scale, the effects of the impact. For several years, scientists have built particle accelerators of colossal dimensions. Often of a circular shape, these accelerators sometimes have diameters several kilometers wide. They can project particles against a stationary target or accelerate them against each other at speeds approaching the speed of light. Collisions produced in these giant accelerators produce enormous energy. This brute energy creates new particles of matter which are sent in all directions. These experiments have revealed the existence of a myriad of new matter particles, until now unknown to physicists. Physicists noted that the protons and neutrons of atoms, which were believed indivisible, are in fact made up of other smaller particles, quarks. Each proton and neutron is composed of a group of 3 quarks that cannot, however, be separated. The electrons belong to another group of particles, which physicists have called leptons. Currently, quarks and leptons seem to be the ultimate components of matter. For their part, the 4 forces of nature would act through the flow of particles called photons, bosons, gluons, and gravitons. Some of these particles are already known to physicists, but others remain to be discovered. Particle accelerators enabled scientists to make another surprising discovery, that of antimatter. Each particle of matter seems to be associated with a twin particle of antimatter. When a particle and its antiparticle meet, they disintegrate, releasing a vast amount of energy. Every day, antimatter is produced and studied in major physics laboratories. Physicists are finding reality, as revealed by these experiments, to be increasingly complex. In spite of this, the physicists believe that this complexity is merely a mask, that the universe is basically simple, so simple that it could be expressed by a single mathematical equation. According to what is called the Grand Unified Theory, a single force existed at the time of the Big Bang, the colossal explosion that created the universe. As the universe cooled, that primordial force produced the 4 forces that now govern our world, together with all the particles of matter that make it up. With their mammoth accelerators, scientists have managed to reproduce conditions close to those existing less than 1,000th of a second after the Big Bang. The results obtained have already enabled them to describe the electromagnetic and weak forces in a single theory, thereby reducing the number of known forces from 4 to 3. Physicists are attempting to expand that theory to include the other forces. They are far from achieving that ultimate goal, but more than ever before, they share Albert Einstein's view that the most incomprehensible thing about the universe is that it is comprehensible. This is an excerpt from a sacred Hindu text. That moves, and that does not move. It is far, and it is close. It is inside of all this, and it is outside of all of this. Today you might hear almost the same thing uttered by a physicist.